In this video, I'm going to show you how you can use an IR distance sensor without a microcontroller. A couple weeks back, as I was lying in bed trying to fall asleep, unsuccessfully, a crazy idea occurred to me. It is entirely possible to build a robot without using a microcontroller. No Arduino, no Raspberry Pi, nothing. Immediately, ideas started flooding in my head on how this robot could be designed. I was seeing pictures almost of how the robot would sense things, how the robot would move, how it would react to everything. These thoughts were so persistent I had to get up and sketch a design. I couldn't fall asleep. I sketched a hasty design because I was really tired, and then I went back to bed. The next day, I decided on some constraints for this robot. The first is that I can't use any form of a microcontroller or a microprocessor. Like I mentioned earlier, that means no Arduino, no Raspberry Pi. But that also means that I can't use any of the chips made by companies like Atmel with their ATmega and ATtiny chipset. I can use them as testing tools, but they cannot make it to the final robot design. So if I need to test out any sort of signals or anything, I can use those as some sort of tool. The second rule I came up with is that microchips are fine, but breakout boards are not. This effectively limits my options to DIP packages, dual inline package chips. So I can't use any surface mount solder chips. I have to go with breadboarding chips. The third is that I can't use my computer to program anything. I can still use double EEPROMs, but if I want to use them, I have to program them by hand. So I'm probably not going to use double EEPROMs. My computer can only be used for the design, it cannot be used to program anything. And the last one is I'm setting a budget of $100. With these constraints in mind, I decided that the simplest robot I could make was an OR, an obstacle and wall avoiding robot. You can certainly design a much better OR using a microcontroller and a few basic parts outside of that, but I thought it'd be a fun challenge to make one without a microcontroller. So, the basics of an OR is that it needs to be able to detect an object, it needs to be able to stop before hitting the object, then turn right or left, and move in a new direction, all the while avoiding any sort of obstacles or walls. This means that the basic components to make an OR work are some sort of sensing circuit that can find obstacles and walls, some sort of locomotion, motors, servos, whatever, that can make the robot move, some sort of logic circuit that tells it how to react, how to move whenever it detects an object or a wall or whatever obstacle is in the way. I decided, based on that I was going to split this up into a couple different sections. The first section is the sensing circuit. How does it find objects, walls, obstacles, whatever. The second is the locomotion circuit. How does it physically move? How does it control that? The third is the logic circuits. How does it react to things? How does it take the input from the sensing circuit and translate into that into signals for the locomotion circuit? And the last one will be the chassis and any miscellaneous circuitry, such as power supply or whatever. The chassis will be more of the physical build of it and the demo. For this video specifically, I'm going to walk you through my design process for the sensing circuit and end with a demonstration of the circuit that I designed. This robot needs the ability to see objects in front of it so that it doesn't go crashing into things. There are many different sensors that can accomplish this, but I decided to go with an IR sensor made by Sharp, mainly because I had it around. It's also a cheap sensor, so it's not too difficult to attain and it's well within budgets. This sensor works by encoding a distance as an analog value. When you graph the distance in voltage, you get a curve that looks like this. For our particular use case, the exact values don't matter much. We don't need to know exactly how far will output what voltage. The important thing is that we need to know is that as the distance increases, the voltage decreases. If you're interested in learning more about this curve, I'll link the datasheet to the sensor in the description below. The only potential hiccup we'll face is if you'll look at the beginning of this graph here, we get unreliable data at close proximity to the sensor. So we need to make sure to avoid letting the robot in such a situation in our design. The way a typical microcontroller would handle a sensor like this would be by sampling the analog output from the sensor and then running that through an ADC, an analog to digital converter. This will produce a value between 1 and 255, and that value can be used in the program to determine what to do. I initially thought of mimicking this behavior, but that turned out to become an overly complicated circuit. It's a topic I want to revisit in the future, but it does involve generating an SPI signal without a microcontroller. It's a pain in the butt. It's entirely possible, but much more work than I was expecting. Not only that, I would then have to respond to a 10-bit word, which would overcomplicate the logic circuit as well. I actually went to the effort of creating an entire timing chart for the SPI signal that I thought I was going to need to record all this. But I had an epiphany. All I needed to detect was if the robot was within a certain range or threshold of an object. So I need a circuit that will output a 1 if the robot is allowed to move forward, and a 0 if it needs to stop. Luckily, a comparator circuit solves this problem. Both of our problems actually, because it is a simple circuit and it will output a 1 or a 0. I can use an op-amp as a comparator. Usually these are used to amplify analog circuits, so for example, as an amplifier for an audio signal, but if wired correctly, they will output the reference voltage if the inverting input is greater than the non-inverting input. I can utilize this. I just need to connect my sensor output to the inverting input, set the reference voltage to 5 volts, and connect a potentiometer to the inverting input. This allows me to fine-tune the distance threshold. As a result, I end up with a circuit that looks like this. Now all that is left is to put it together. The specific chip I'm using is the LM3582. This package contains 2 op-amps, but I will only be using one of them. The pinout is given in this table. I start by connecting pin 8 to 5 volts and pin 4 to ground. My output will be on pin 1, so I add an LED there with a current limiting resistor to ground. Next, I add a potentiometer with one leg tied to ground, one leg tied to 5 volts, and the output goes to pin 3, which is the non-inverting input. Lastly, I wire up my sensor. The analog output goes to pin 2, the inverting input. VCC goes to 5 volts, and ground goes to ground. As you can see from this demo, whenever I put my hand over the sensor, the LED will turn off. When I take my hand away, the LED turns back on. I can adjust the threshold where the LED will turn off with the potentiometer. This will be useful later when we want to know if the robot should be moving or not. I hope you liked the video. I put links to the products I used in the description below. Be sure to check it out. I'm experimenting with different delivery styles at the moment, so be sure to let me know down in the comments how effective you think this style is, and how you think I can improve it. And lastly, be sure to subscribe so you don't miss the rest of the series where I design and build a robot without using a microcontroller.